Okay, in the last video we covered the modern non-parametric statistic tests, and we concluded that while they are cool conceptually, they are probably not necessary. So in most cases you can transform or simply ignore assumption of normality and homogeneity of variances. And now we'll cover the classic tests, the rank sum based tests. They're even less useful. So under normal circumstances, I wouldn't recommend to use these rank sum based tests. There's one notable exception, and that is if you are really after the median. So if the median is the statistics that you care about and the mean does not matter, then your rank sum based tests are the statistical tests of choice. But we'll go over this at the end of the video, that this rarely applies. So normally, even for non-normally distributed data, the mean tends to be the statistics that matter. I will show you an example where the median does matter. But if you test for medians with these techniques, you also lose a lot of statistical power. So these tests are not able to perform as well as a permutation-based test. So in normal circumstances, you would either go for the permutation-based test, and we already established that if you use that, you might as well go with parametric statistics. But in any case, for that one exception where you want to test medians, this is actually an interesting technique. It's been developed in the 1940s, and the idea is kind of similar as a permutation-based one. So you also do permutations there, but you can do them with pure math. You don't need computers. You can use combinatorics to figure out your distribution of the rank sums. That is pretty clever, so it's very satisfying to understand how this methodology works. Okay, so let's see how the classic non-parametric tests work. So these are rank sum tests, and rank sum really reveals how this works. So let's say we have an equivalent to a t-test situation like we had before, two varieties and some measurements of yield. And we want to test for statistical differences, but we observe there's an outlier or something else in our distributions that we don't like. So we decide to go with the classic non-parametric tests. So what goes on behind the scene if you ask that test to be executed is the following. So the first step is that you simply rank your observations. So by ranking, you kind of equalize any weirdness that may go on with distributions. So if I rank them from the highest to lowest, I start with my outlier here. That's the biggest one, and this is the second biggest. 630, 420, that's number 5, and that's number 6. So those are my ranks from the biggest to smallest. And now I calculate the sums. So for treatment A, that would be 1 plus 2 is 3 plus 4 is 7. And for treatment B, 6 plus 5 is 11 plus 3 is 14. And now we calculate the difference. So 7 minus 14 equals minus 7. So that is my rank sum difference. And obviously, the bigger the rank sum difference, the less likely it is that this happens by random chance, right? So if you line up all the observations for treatment 1 in the top group and all the values for treatment B in the bottom group, then that's less likely to just occur by random chance. So here we still have a fairly big effect, it looks like. So we got one switch, so the maximum we could get is 1, 2, 3 in one group and 4, 5, 6 in the other, but the 3 appears down here and the 4 appears up there. So the two intermediate ones are exchanged. So the bigger those differences, the more likely it is that my effect is not due to random chance. So if I were to just jumble this up and calculate rank sum differences like we did in the permutational ANOVA, our expectation would be that the rank sum difference is something close to 0, right? So these numbers would be roughly the same, this one and this one, and then one minus the other would be something close to 0, not exactly 0. So that would be our expectation. So if we look at a distribution of, let's call those random rank sums it would be, around here. If we did another one, if we observed them, they would just accumulate here at the middle, and as we add more permutations, we would build this distribution that would probably look like a normal distribution, and then we could check where the -7 that we got up here, where that sits. How likely is it that I get a value that's as small or smaller than a -7? Or if I do a two-sided test, what's the probability of getting a value that's either smaller than -7 or bigger than 7? So that's what we want to know. That is the probability we want to calculate. And this is actually something you can do with combinatorics. So you can use combinatorics to derive exact p-values. And to illustrate this, I'm doing an even simpler example here. I'm just going with a sample size of 2 here, so 2A treatments, 2B treatments, and I calculate my ranks here, 1, 2, 3, 4, and do my rank sum. So in this case I have 7 minus 3 is 4, and that's my rank sum difference, just as we had it up there. I'm also giving those an ID, and I could now, rather than empirically permutating this and calculating the rank sums, this is actually a math problem that is regular. So because you don't have to deal with all those different values like I would in a permutation or ANOVA, there's no way I can calculate anything in advance. But in this case, this is a problem that I only have to solve once, right? So if I once calculate all the permutations that are possible in these ranks, then I know what my distribution of those rank sum differences is. So this distribution here, I basically calculate for every single possible combination that I can have. And those are many if I work with a large sample size. But this can all be done with combinatorics. These are formulas like this, right? So if I have a sample size of n equals 4, then I have 4 factorial combinations, how I can arrange those rankings. So 4 factorial is 1 times 2 times 3 times 4. So this would be 24 possible combinations. So I'm just going to put the possible rankings here. So we could have 1, 2, 3, and 4. So this would be just one way to possibly rank them. Now I can switch up the 1 and 2, and I have 2, 1, 3, 4. Or I could switch up the 3 and 4 down here. So then I would have 1, 2, 4, 3. And I can switch up the 1, 2 again. So I could have 2, 1, 4, 3. So I could have 4 ways to arrange the treatments A and B, so that the rank sum here would be 3 minus 7, so 3 for A, 7 for B, and the rank sum difference would be minus 4. And that would be the same for all of those. So minus 4, minus 4, minus 4. All right, that's my first block here. Now what else could we do? We could switch the 2 and the 3 here, right? So let's do this. 1, 3, 2, 4. So now again I could switch the 1 and the 3. So I got 3, 1, 2, 4, and so on. And I get again 4 ways to arrange this. So in this case my rank sum differences would be 4 and 6. 4 minus 6 is minus 2. So I have 4 ways to get a minus 2. And so on. So I can continue this. So the next one, the next block would get me zeros, and then I get another block of 2s, and then I get another block of 4s. So just by switching the 3s and the 4s to the top and calculating all the combinations. So what I do here in this weird way, there are clever ways for somebody who knows math well. They can figure out those possible combinations and what their frequencies are out of those 24. So if I were to plot this out, my distribution of the rank sums for this super simple example, this would actually look somewhat like a normal distribution. It doesn't quite, because the sample size is just too small, but if you have a larger sample size, it would approach a normal distribution. So that's what I would expect by random chance. So if I get a rank sum in my original experiment of 4, I can now read off my exact p-value. So if I have a rank sum of 4, that's exactly a 4 over 24 chance. So it's a 1 out of 6 chance, and that's a 0.1666. And that is my p-value for a one-sided t-test. Or if you were to do a two-sided t-test, then you would also consider the other side. So we covered this when we did the t-test. So you're asking what's the probability of getting a rank sum that is either larger equal 4 or smaller equal minus 4. So in that case, the probability would double. And you can try this out. This is something you do a Wilcox rank sum test with this data table. You can enter this manually actually. And so just A equals, concatenate 536 and 625, and the other one doesn't matter what numbers you put in there, and then just run a Wilcox test in the lab with just these numbers, and you will get exactly that result here. So you will get a p-value of 0.1666. So this is how these tests work. It's such a nice illustration of how statistics works, right? So you're coming up with these distributions of random expectation, and then you have your signal to noise ratio, which is in this case a rank sum difference, and you ask, what's the probability of getting a signal to noise ratio is big or bigger by random chance. So all these tests are based on the same conceptual principle, but they are not as good. They will not give you the same statistical power, so the p-values here will always be larger. And the reason is also quite clear, because they don't consider the magnitude of the observations, right? So in this case, let's say my actual yield values were, let's keep those values, so 500 and 600, and then for my treatment B, they would be 700 and 800 or something like that. So then they would rank 1, 2, 3, 4. But the same rank could be also achieved by an experiment that has 500, 600, and then here 5,000 and 5,100, right? So that difference, that magnitude difference, is completely ignored by the rank tests. So they would rank in exactly the same way. No difference regardless of the magnitude, as long as I ordered the same way. So that removes some of your power and some of your confidence that you can get with parametric statistics that actually would consider the variance within and the big variance between, right? And that would give you the high confidence and the really small p-values in a parametric statistical test. So these are just for fun, and not, but don't use them. Or maybe I should slightly qualify this and say don't use them under normal circumstances. So in some cases, if you're after the median, the rank sum tests are actually the only way that you can get the answer that you want. And to illustrate this, I show you a little sample data set where we can look at the median and see what different techniques, general linear model, the permutational analysis of variance, and the Wilcox test would make out of it. Okay, let's see if we can run this. So we read in the data, attach it here for simplicity, and it's simply that we have a simple treatment effect here, A and B, and a dependent variable Y. We can look at the whole thing. So there's A and B values here. We can also look at a box plot, how the data look like. So there we have it nicely arranged. And so I created this data set so that it's kind of a zero inflated data set with really long tails. But what I did is I set the median to almost exactly the same value here. And I do this just for illustrative purposes, so they obviously could be slightly different and you would get pretty much the same result in what follows here. But you see that while the median are the same, the distributions are definitely diverging here, so I have a much longer tail in one treatment than in another. And that's actually a very, very common kind of situation where you have a dependent variable that's distributed like this. In some cases, once things get going, they really get going. And otherwise they stick around at low values. I don't know what good examples could be, but maybe maybe some sort of fungus that attacks a crop. So once it overwhelms the plant defense, then your number of lesions go up like crazy. But if it doesn't overwhelm the plant defenses, then it stays at the low end here. So now let's see how our tests would evaluate this situation. Let's start with a linear model, and we just do an ANOVA, and it gives me 0.037. So a significant effect if 0.5 is your threshold. Of course, we really violate the assumption of normality here, but hold on, we know how to fix this. We can run a completely different analysis. So let's check it out. Permutational ANOVA. So same code essentially, just with a different function that does something completely different. And check this out. So it's 0.31. That's the real answer. 0.37 is wrong. So again, I like to emphasize that linear models are extremely robust against violating assumptions of normality. And also these kind of differences here, 0.37 versus 0.31, this is actually just due to this being a random permutation. So it will give you a slightly different answer every time. And it actually centers around the 0.37. So in reality, these will give you, in the long run, exactly the same result. So I can run this again here, and you'll see you get a slightly different p-value. So this time, we actually got a slightly lower one. But if we do this again, now we got 0.46. So you can see that is really the same as what we would get out of the linear model. But now let's see what the Wilcox is going to make out of this. So can you guess what the Wilcox will say? The Wilcox is rank-based. So if I don't know the magnitude, I have exactly the same amount of observations above the median as I have below the median, right? So this one should not surprise you that it says no effect. In fact, it finds exactly the 0.5 here because the medians are almost exactly the same, and there's an equal amount above and below the two medians in the two treatments. So I like to note that if you follow the rules like they are taught in every other statistics class, right? If you have these zero inflated distributions, and you should definitely not use parametric tests, rather use the rank sum tests. And that is what everybody does. What's your inference here? So let's pretend A is a fungicide that I'm testing, and B is my control treatment. So in my control treatment, some of the plants get really attacked, and in my fungicide treatment, that is really reined in, right? So if I follow the Wilcox, it would say, well, there's no evidence here that the medians are different. And in fact, there is not, right? So median is not different. But the permutational one and the linear model one will compare the means. And so this usually is a meaningful difference. Let me think of another example. Let's say this is a medical trial, and they want to test a drug that lowers cholesterol. So in this case, let's pretend that B is your before treatment and A is your after treatment, after you give the drug. Or you could do a placebo trial where B is a placebo and A is your drug. And you're asking, is this drug effective in lowering my cholesterol levels? So if you follow the rules, you would do the Wilcox test and you would say, no, this medicine is not effective in lowering your cholesterol. But in fact, actually does what you want it to do, right? So it reins in the high cholesterols just perfectly. So you really have to understand what these tests do in order to avoid those pitfalls. So you can't just follow those rules that are taught. 90%, this is going to be a train wreck. So you really have to think about how the statistics work, right? So this really helps. Once you know what that does, then you know that it can't detect these kind of things. Now, I said that there are cases where you are after the median, where the median matters, right? So let's pretend this is a economic experiment, and I create some policy to raise the median income of a certain region. And let's say in this case, this is my before treatment here, and this is my after treatment. And I'm asking, has this policy made any difference? And, it surely has not made a difference in your median income. So only the rich people get richer. And the poor people, they actually get poorer or stayed the same. So the median has not changed at all. And so in that case, the Wilcox will give you the right answer. And these ones here, they will not. So they will not give you the correct answer. So if you're asking, has the median income been improved? Because that's what you were after. That's what the policy was designed to deliver. Then the answer is that there is absolutely no evidence for this policy to be successful. So in that case, the Wilcox is the one that gives you the right answer. So again, I like to emphasize, don't follow any recipes. You really have to understand how the methods work, and I hope this course contributed a little bit to this. So go ahead and try all this out, both the modern and the classical non-parametric statistics. So there's actually a number of variations of the rank sum based tests for slightly different purposes. And so have fun with this lab.